65, and we conclude with presentation number 68. We can begin with Madame Zemzemi Maria.
Thank you, Madame Aitiesin. I will share my screen, please.
Yes.
Can you see my screen?
Yes. Okay. Go ahead, please.
Thank you. Bismillah ar-Rahman ar-Rahim. Hi, I'm Maria Zemzemi, a Moroccan doctor. I hope that you're safe and in good health. So the presentation will be on a proposal multi-agent, sorry, it's okay now. So the presentation will be on a proposal of a multi-agent modeling based on a parallel model of the PSO algorithm. It is a scientific contribution both to the Sultan Moulay Slimane University and Ibn Tofal University here in Morocco, and also to the Normandy University in France. Our outline is as follows. We have two main parts. The first one is an introduction of the PSO method, and the second one is about our proposed approach based on the PSO algorithm. The task of optimization involves determining the measure of optimality subject to certain constraints. Optimization is of utmost importance in every field, since everyone is interested in finding the optimal value subject to constraints, for example, cost and efficiency. The term optimization refers to either minimization or maximization. Of all the available optimization methods, PSO is a very known meta-heuristic method, often used to solve complex engineering problems, such as structural and biomechanical optimization. It was proposed, it is inspired from the nature, social behavior, and dynamic movements with communication of animals, like insects, birds, and fish. Proposed by James Kennedy, psychologist, and Russell Eberhard, electrical engineer, for solving continuous and discrete optimization problems. It uses a number of agents, named particles, that constitute a swarm moving around the search space looking for the optimal solution. The basic PSO algorithm can be summarized as follows. So we initialize the swarm by giving initial locations and velocities stochastically assigned. The positions of the particles must be randomly distributed in the search space. We evaluate the fitness of each particle. Then we update individual and global bests. After that, we update velocity and position of each particle. We go to step 2 and repeat until the stopping criterion is met. PSO has a number of related parameters that determine its behavior and effectiveness. The choice of the used values for these parameters affects greatly the PSO performance. We have, for example, the swarm size, it means the number of used particles, the dimension of the problem, depending on the objective function. Communication topologies are employed to interconnect the swarm, etc. Each particle adjusts its traveling speed dynamically, corresponding to the flying experiences of itself and its colleagues. Each particle modifies its position according to 4 elements. We have its current position, its current velocity, the distance between its current position and its personal best solution, and the last element is the distance between its current position and the global best solution. The change of the velocity is performed using a new term in the equation. It was introduced by Bushnack and Forrest in 2006. This is the best position of the neighborhood. Even if PSO is a very robust meta-heuristic, but it's like all evolutionary methods, PSO has a number of disadvantages, and our study focused on finding solutions to the two essential disadvantages of PSO algorithm: premature convergence and computational time. This picture is a representation of the flowchart of our PPSO model, parallel PSO model. In our approach, we began, I will use the mouse, it's okay. So, in our model, we began by initializing the search space by a set of particles through the assignment of their initial positions and speeds, and also communication topology. Then we create neighborhoods by a radius value. After that, the processing of each neighborhood is attributed to a thread. Our model is based on parallel processing. In fact, processors have to perform calculations on groups of particles and neighborhoods. So we start the processing of all threads in parallel for an iteration. Then we update the neighborhoods according to the new positions of the particle and the new value of the radius. If the stopping criterion is satisfied, we stop the program. Otherwise, we start the processing of all threads in parallel for a new iteration. The result is the best solution obtained among the threads. Our approach is designed for complex optimization problems with a large search space and several local optima. And the main objective is to make a better exploration and exploitation of the search space. For this proposed model, the neighborhoods are dynamic spheres. This is an example of the distribution of particles in the search space in 2 dimensions. With each iteration, the number of particles included in the different spheres changes according to the new positions of the particles and the value of the radius. Like all evolutionary algorithms, PSO has a set of parameters which is to be defined by the user, and our PPSO program has a user interface where the user can choose all the PSO parameters according to the user need. For example, the definition of the global search space, the dimension of the optimization problem, the number of used particles, the communication topology, etc. For the present study, the list of the used PSO parameters, which gave during the experiments sufficiently good results, are mentioned in this table. For example, the number of particles, we have 30. The number of iterations between 50 and 80, depending on the objective function. Communication topology, we use the ring topology. The choice of the radius value is very important because neighborhoods are created using this value, and a very large radius value is equal to a small number of neighborhoods, while a small value is equal to many. So the choice of this criterion remains critical and depends on the problem to be optimized. To test our proposed parallel model, a set of 10 test functions has been selected to evaluate the performance of our parallel model. Here we have the description of the used functions. The presented results are related to a set of 10 test functions Each function contains a number of local and global minima. For these experiments, we used an average of 1,000 function evaluations. The programming language used is Java. Threads are the technology used in Java to make multitasking as applications. We were interested in this technology to take advantage of parallelism in terms of reducing computation time and better use of material resources of the machine. According to the results, we can say that the PPSO algorithm provides the optimal solution with a higher probability, and the computational time in our proposed model is lower than the basic PSO and the two other PPSO models. The graphical results are illustrated in these following figures. We have here the average time for the basic PSO and our proposed model, and two other PSO, parallel PSO. Here we have computational time, and here the success rate. Our proposed model is in line, red line. In order to ameliorate these results, we add the multi-agent system to our proposed model. The swarm is considered as a multi-agent system. Each particle is considered an agent, the neighborhood is an agent, and the environment itself modeled as an agent. The combination of multi-agent system with parallelism for solving complex optimization problems allows speed calculations and gives the particles more autonomy in order to have a more optimal convergence. Our proposed approach consists of giving particles more autonomy, asynchronous execution, and superior learning abilities. The environment would be transformed into a more dynamic and informative research. As a conclusion, by analyzing the advantage and disadvantage of the standard PSO, our approach, based on maintaining a balance between exploration and exploitation of the search space and parallel computation, is proposed in this work. Our model introduces a right balance between exploration and exploitation by starting in parallel the PSO algorithm for each neighborhood independently in order to increase the probability of jumping out of the local optimum and minimizing computational costs. Our algorithm was tested on 10 benchmark functions, and from the experimental results of these functions, it can be seen that our proposed algorithm performed much better than a basic PSO algorithm and other parallel PSO models on the selected problems. In the future, further tests will focus on testing the performance of our approach in a multi-core machine in order to well exploit cores, and we suggest to test this proposed approach in a real optimization problem. This is our references, and thank you for your attention.
Thank you very much, Madam Zemzani. And now, if someone has any question,
I have a question.
Please. Okay.
Okay. Thank you for explanation and clarification in your presentation. I have a question, two questions or three. The first one is what is the difference between your approach, PPSO approach or MAPSO approach, and the other work in like Arjen in 2060 or Andrew in 27, and how did you choose your parameters, and where is your modelization? I didn't find modelization in your work. The main idea of my question, what is your added value? And thank you.
Thank you. Thank you, Mr. Mohammed. So for your first question, it is about our proposed approach, parallel PSO. So the difference between our approach and the others. First of all, before starting modeling our approach, we make a benchmark of all the existing parallel model based on the PSO algorithm. And we have also some other parallel models based on the PSO algorithm. But our last version is this model. And the difference is the use of threads, which is used different. It is different. That's how it's used in other models, and the use of dynamic neighborhoods, which is a new use of neighborhood, because in a basic PSO, there is no neighborhood concept. But in 2006, this new term is added in the equation of the movement of the particles. So we add this concept of neighborhood, but by using dynamic neighborhoods and creating neighborhoods like spheres. And this approach, by linking dynamic neighborhoods and parallel computing, gives superior results in comparison between others models based on PSO algorithm. So this is my answer for your first question. The second is, I think, about
find the parameters.
Parameters. So as I mentioned before, so the added value is the modification in our approach concerns three elements. We have the concept of parallelism by using threads, evolutionary neighborhoods, it means dynamic neighborhoods, and the adaptation of the PSO parameters by making a lot of experiments to have the adequate parameters available to each objective function, means each optimization problem.
So how many experiments to define the better parameters, which the better parameters to choose?
Mr. Mohammed, there is no number. For example, for us, we used for each function 1,000. I mentioned in my presentation 1,000 evaluations functions for each function, and we change in every time the each parameter. For example, the acceleration, the coefficient of acceleration, and the number of used particles, the number of iterations, and also the stopping criterion, because it is a very important important criterion. The stopping criterion plays a very important role in the program. So we did a lot of experiments to have these results.
Okay.
Thank you.
Thank you.
I have a question.
Yes, please.
First, thank you for your presentation. It is very clear. I just want that I see that in your presentation you talk about parallel model or some kind of parallel implementation. Could you please share with us the parallel application programming interface that you have used and what is the multi-core platform that you have studied? And if you have performed a parallel implementation, what is the speed up that you have obtained? Thank you.
Thank you, Mr. Abdessamad. So for your question, as I mentioned in my presentation, we used Java for parallel computing. Can you hear me?
Yes, I hear you. Go ahead.
Okay, so we use Java, and the threads are the technology used in Java to make multitasking applications. So we're interested in this technology to take advantage of parallelism in terms of reducing computational time and the better use of material resources of the machine. And as I mentioned in our perspectives, in the future we suggest to test our proposed approach in a multi-core machine in order to well exploit cores. That is the objective. It is our objective in the future. It's our perspective.
Okay, thank you for your response.
Thank you, Mr. Abdessamad.
Okay, thank you, Mr. Mohammed. Thank you, Mr. Abdessamad. Thank you, Madam Zemzami. I think we continue with the other papers. The paper ID number 161.
Thank you, Professor Ait Yassin. I will just share my screen.
Okay.
Can you see the presentation?
Yes, okay.
Okay, so good afternoon, everyone. I hope that everybody's doing great. So my name is Zadine Nohila, and I'm a PhD student from University Hassan II Casablanca. My research interest is centered around the combinatorial optimization problems and especially routing problems. And in this work, we will see a discrete path algorithm for the multi-compartment vehicle routing problem. The presentation will go as follows. After the introduction, the first part will be dedicated to the multi-compartment vehicle routing problem, MCVRP for short, and the second part is for the path algorithm meta-heuristic. After that, we will discuss the approach we use to solve our MCVRP, and some numerical results will be discussed. Before moving to the multi-compartment variant, let's see first what is a vehicle routing problem. So vehicle routing problem is one of combinatorial optimization problems that aims at finding an optimal set of routes for a fleet of vehicles in order to solve a given set of customers. And what we mean by an optimal route, it's a route that minimizes the transportation costs and maximizes the value. This problem has many variants, and among these variants, we have our multi-compartment variant. What's particular about this variant is that we have a fleet of vehicles that are compartmented so that we can transport different types of products in the same vehicle, even if they are incompatible. This problem was used to model many problems rising from many industries, such as petrol station replenishment, different oil types transportation, collection of different types of milk, distribution of animals' food, and garbage collection. Over the years, there has been many works that tackle the MCVRP, but to the best of our knowledge, just a few works approach the problem using swarm intelligence. And here are some of these works. We have Abdelkader et al. In 2015, he used a hybridized ant colony algorithm to solve the problem. And Chen in 2019, he proposed a hybrid particle swarm optimization with simulated annealing. Now let's move to our mathematical formulation, and here is the assumption we used in the model. So we considered that the fleet is homogeneous. The vehicles have multiple compartments. Each vehicle starts and ends at the depot. Each product is assigned to one compartment, and which means that the number of compartments is equal to the number of products. Demands of all customers must be fully met. And each customer is served exactly once by a single vehicle. Here are the notations we used in this model, and let's move now to our decision variables. So in order to effectively model this problem, we designed 3 decision variables. The first one is a binary variable that takes 1 if vehicle K visits customer J from I and 0 otherwise. The second one is also a binary variable and takes 1 if customer I receives product P from vehicle K. The last one is a continuous variable that indicates the remaining quantity of product P in vehicle K after leaving customer I, and this one will be useful for the subter elimination. Our objective function is, of course, the minimization of the total traveled distance and subject to this constraint. So the first constraint imposes that vehicle K visits customer J from I only once. The constraint 3 is the continuity of route K. Constraint 4 is the capacity constraint taking into account each compartment. And the constraint 5, it's to ensure that the demand of client I must be fully delivered by the same vehicle. We don't allow split deliveries. Constraint 6 and 7 are for the vehicle to start and end at the depot. Constraint 8 and 9 is for structure elimination, and finally, the decision variables that are binary. Here is the altogether mathematical model, and let's move now to our BATH algorithm meta-heuristic. BATH algorithm was firstly introduced by Young in 2010, and it was inspired by the echolocation behavior of microBATHs. Thus, the BATH algorithm was developed using 3 idealized rules. The first one is that all bats use echolocation to sense their prey's location, and they can distinguish between food and obstacles even in the dark. The second one is that bats fly randomly with a velocity vi at position xi with a frequency, a loudness, and a pulse rate. And the loudness varies from a large positive value to a minimum value. So we can summarize the BATH algorithm steps in 3. Namely the diversification, intensification, and the selection phase. The diversification phase is provided by the velocity, and this updates equations. We have first the frequency, that is a random number between a minimum and the maximum value. Next is the velocity that is updated using the previous one, plus the distance between the current bat and the best bat in the population times the frequency. And the position is updated using the previous one, plus the velocity we just updated. For the intensification phase, it consists of a random walk, and depending on the pulse rate, a locus search is applied to the best solution in the population, where epsilon is a random number between -1 and 1, and A index T is the average loudness at iteration T. A selection phase was developed in the BATH algorithm to improve the solutions over iterations. So BATH algorithm selects the fitter solution to replace the less fit one with a probability AI, which means that if this condition is met, we then can accept the new solution. And in order to balance between exploration and exploitation, if we accepted the new solutions, we can increase the pulse rate and decrease the loudness using this update equations. Now here is the pseudocode of our standard path algorithm. We have the first, the initialization of our parameters and variables. Next, this is our diversification phase where we update the frequency, the velocity, and the position. Here is the random walk that depends on the birth rate, and it is the our intensification phase. Next is the selection phase, and without, of course, forgetting to rank the paths and update the current best path over iterations. Now let's move to path algorithm in discrete optimization. It has been applied in many problems, and they are categorized in 5. We have scheduling, routine, facility-like design, allocation, and combination of these problems. We are interested in routine problems. So here is some of interesting works in this context. We have Sergi et al. In 2016. They proposed a novel discrete path algorithm for solving the symmetric traveling salesman. And inspired by this work, we have Osaba et al. In the same year. He improved the discrete path algorithm to solve the symmetric and asymmetric traveling salesman. In 2019, the Osaba et al. Proposed a discrete path algorithm to solve a variant of vehicle routing problem rising in the medical goods distribution. The latter work is what we adopted in this study, and here is how it works. First, the solution encoding we used is the permutation codification. For example, here is a solution that has 3 roots, and the roots are separated by 0 that stands for the depth. Just like the original path algorithm, the 3 steps of the algorithm are maintained, but some modifications were needed to prepare it for discrete optimization problems. For the diversification, the velocity was adopted using Hamming distance between the path I and the best path of the population. So it is a random number chosen between 1 and this Hamming distance. And for the position updates, 2 operators were used. The first one is the insertion function, where we choose a random node and we reinsert it in a random position. And the second one is the exchange function, where we choose 2 random nodes and we exchange their positions. It is to note that the frequency was not taken into account in this discrete path algorithm. For the intensification phase, it consists of a local solution generated around the best solution and using either the insertion or exchange function we just explained. As for the selection phase, no modifications were made, and the update functions of the pulse rate and loudness remained unchanged. But to enhance the exploration capability of the algorithm, Osaba et al. Proposed an effective method. For a path to move, it should examine its velocity. If it is greater than half the customers we have in the problem, it needs a large move. It means that it is far from the best path in the population, so it needs a large move, that is the exchange function. Otherwise, it is a promising solution, so it will perform a short move, and that is the insertion function. Here is the pseudocode of this adopted discrete path algorithm. We have here the initialization of the parameters. Here is our diversification phase, and here is our intensification phase, and finally the selection phase. Now, the approach we used to solve the multi-compartment vehicle routing problem was to adapt this discrete path algorithm to the constraints of the problem. For the initialization, we used the randomized Clark and Wright algorithm to generate the population, and a function we called isLoadable was implemented to ensure that the capacity constraint is respected, and also to ensure that the products are loaded to their dedicated compartments. Here is the pseudocode of our isLoadable procedure. It takes as input the orders of of customers in the route we want to check its feasibility and the compartment size. So for each product, it checks if the cumulative demand of each customer doesn't exceed the compartment size. If it does, it means that our our route it's not feasible and we won't accept it. Before moving to the numerical results, here is the parameter setting we used in both our path algorithm and the GRASP. GRASP stands for Greedy Randomized Adaptive Search Procedure. It is a single point-based meta-heuristic. So for the sake of fairness, we thought that we should use a large number as a maximum iterations, unlike in path algorithm. The problem instances here were generated using the procedure described in Abdul Qadir et al. And as you can see, we have the number of customers is different. And analyzing the given results, it is clear that the quality of the solutions given by our path algorithm are of a better quality than the ones generated by the GRASP algorithm. Besides, the difference between the two generated solutions is clearly important. The improvement percentage is about 25%, and 25% as a number is significant as it represents the savings generated in terms of transportation costs. Studies still have to be carried out about computational effort, but in general, the results are satisfying and motivate the continuation of this work. Overall, it may be said that the path algorithm is a promising algorithm that showed to be efficient, and applying it to the multi-compartment vehicle routing problem was a good choice. But to complete the work, we still have to improve our discrete path algorithm and do some more experiments on more complex models of the MCVRP. We should compare it with other swarm intelligence algorithms, and we should consider the hybridization of the algorithm with other meta-heuristics to further improve its performance. Finally, here is the references we used in this work, and thank you very much.
Thank you very much, Madam Nuhaila. If someone has a question, please go ahead. Hello, has someone any questions for Madam Nuhaila? Nuhaila?
Yes.
I will ask a question. What is, please, the added value for your research?
Okay, so my added value is that we actually applied the path algorithm to the variant of vehicle routing problem called the multi-compartment. Yes. And we used for the initialization a random algorithm, construct a random algorithm called the randomized Clark and Wright.
Yes.
Besides, we implemented a procedure called isLoadable that ensures that every demanded product is loaded in its dedicated compartment, as we have compartmented vehicles, and that the capacity doesn't exceed each compartment.
Okay, thank you very much. Thank you, Nuhaila, for your presentation. And now we continue with the paper number 163, Mr. Mohammed Guskir. Go ahead.
Yes, I'm here. Thank you. Hi, everyone. Let me introduce myself. I am Mohammed Guskir, PhD graduate from Sultan University, Laboratory for Sustainable Development, Faculty of Science and Techniques of Beni Mellal. My presentation is about automatic analysis of brain tumor from magnetic resonance images based on geometric median shift. The presentation is structured as follows. starting with an introduction to present the problem and the main contribution. To better understand these contributions, I will present to you the original main shift algorithm, disadvantages and limits. Then our proposal and contributions to remove these limits by considering the image as it resides in a non-Euclidean space. In the fourth point, we will discuss the obtained results, finally a conclusion and perspectives. So the main shift algorithm is a non-parametric algorithm which has been applied to many computer vision problems, such as data clustering, feature analysis, and image segmentation. However, the use of Euclidean distance makes this approach has some limitations. Ineffective in clustering data, sometimes poor results of clustering, and in image segmentation. The challenge facing the main shift algorithm is the adaptive specification of the bandwidth according to the data statistics in the image. So we propose to replace the Euclidean distance by geodesic distance, considering the data set as residing in a Riemannian manifold, and we use the geodesic distance for an adaptive bandwidth. Main shift procedure based on kernel density estimation, which is the most popular density estimation method. The density at point X can be estimated by the Parsons window kernel density estimator as mentioned in the first equation, that where k is a profile function satisfying k of x is greater than 0 and for all x for all positive x. And we define the derivative, the gradient of the kernel density function as mentioned in the second equation, where this equation is to calculate the main shift vector. So the MSA is well-known, non-parametric and unsupervised clustering algorithm, which is not assuming a fixed number of clusters. The main shift is also an iterative algorithm which aims to make a point converge to the nearest local maximum using the following equation. Saddle points can be detected and removed to obtain only the modes. As mentioned in this figure, we start by choosing a point from P. We look for the set A of points which are in the vicinity of P. We place P toward the isobarycenter of the set. We reiterate from step 2 until converge. For data clustering and image segmentation, this algorithm produces sometimes poor results. In clustering data with high dimension manifolds in Euclidean space. I think there is someone share his presentation.
Hello?
Yes, please, Mukhtar.
Someone share now his presentation, please? Not yet. You can continue, Mr. Kuski.
Thank you. Thank you. So we extend the Riemannian manifolds and median shift approaches to perform the automatic detection and segmentation of brain tumor in MRI images. Furthermore, this approach can be used to track the change of abnormalities regions. The geodesic distance for a pair of points C and O distributed on a Riemannian manifold denoted D or G in the minimum length of curves connecting them. As mentioned in this figure, given a set of points distributed on a Riemannian manifold associated with a geodesic distance, and we extend this equation with a geometric median of a data set defined as a set of points by the following equation, which calculates the minimum of the length of the length. So we define a novel kernel density estimate function for the geometric median shift on Riemannian manifolds as follow, where K is a flat kernel function, H is a bandwidth, and C ensure that the density function to be the density kernel to be a density, and phi is another kernel function. This other function is related to the sum of squared Riemannian geodesic distance from started point to the end point distributed on the manifold calculated by this equation. So phi is enforced to be a convex function. Finally, the gradient of the kernel function for geometric median shift over Riemannian manifolds is calculated by this equation, where G is the derivative function. So as you see in this figure, the overflow of the proposed method, we propose to apply an adaptive method that employs mean shifts algorithm over Riemannian manifolds. We propose a better adaptation of the geometric median shift algorithm to detect and segment accurately the region of interest and in magnetic resonance images of brain. This improved adaptation is a combination of geometric median shift with K-means algorithm to detect and cluster the brain tumor regions. The obtained results improve the homogeneity of the both methods. This study addresses to the problems of segmentation of abnormal brain image or abnormal brain tissues and normal tissues such as gray matter, white matter, and cerebrospinal fluid, as mentioned in this part of this figure. So to evaluate qualitatively and quantitatively the performance of our approach, we use the following data set. Brain web contains the MRI volumes for normal brain. The parameters seen are fixed to three modalities: T1 weighted, T2 weighted, and density pattern. 5 slice techniques, 6 levels of noise, and 3 levels of density non-uniformity. And the second one, MRI multiple sclerosis database, which contained 38 patients, 17 males and 21 females. Detection and desegmentation results of brain MRI tumor presented in this figure for different modalities of brain MR images, multi-sequence such as T1 weighted and T2 weighted. The brain image presents different level of noise and spatial intensity in homogeneity for the axial slices. However, This figure shows the good results of filtering and smoothing images using geometric median over Riemannian manifolds. Then we proceed to cluster different regions of smoothed image. The last step is to separate the classified regions of brain tissues into gray matter, white matter, cerebrospinal fluid, and abnormalities regions. As we can see in this figure, representing the obtained results from coronal slice of T2 weighted brain image to evaluate the segmentation accuracy of proposed approach. The proposed method shown the efficient results to clustering brain region and to segment accurately different tissues and tumor regions from a complex slice. To validate the obtained results quantitatively, we use the dissimilarity coefficient. This measure indicates the amount of area overlap between the automatically detected and the manually delineated brain image. The dissimilarity coefficient is calculated the quality of obtained results from different slice orientations and sequence. Analyzing the result of the dissimilarity coefficient, the obtained rate of the T1 weighted sequence from brain MRI images is the better, say 98%, as shown in this figure, for the axial slice and 94% for the sagittal slice. So, due to the complexity on T2 weighted images and high intensity and homogeneity of tissues, we obtained 94% from T2 weighted sequences for the axial slices and 91% for the sagittal slices, whereas the highest rate obtained for axial slices from T1 weighted sequence due to the homogeneity of intensity of pixels and low complexity of brain structures. So, as conclusion, we propose an automatic detection and non-supervised segmentation of brain MRI tumor. The task of this method is to automatically obtain an accuracy segmentation of tissues and check the presence of abnormal regions in those images using geometric median shift over Riemannian manifold to smooth the image, followed by Cummins' algorithm to cluster the regions of interest. This method applied to many images proved that the use of this method gives better results and make it easy to cluster images after smoothing. And in the future work is to use the median shift over Riemannian manifolds algorithm in detection step and machine learning in classification. However, the learning side can increase the rate of the dissimilarity coefficient using the score stripping or the brain extraction regions to eliminate non-brain regions. And thank you for your attention.
Okay, thank you very much, Mr. Guskir. If someone has any question for Mr. Guskir, please go ahead. Has someone any question? Okay, I think I have one question for Herr Guskir. You have segmentation algorithm for magnetic resonance images. Yes. Why not the computer tomography images, CT?
So I use these images for to accurate the segmentation of no homogeneity regions. For tomography images, the quality is less, but for the images of for the MRI, the quality of image is high, and for an exam of MRI, the obtained images are so for 3D images, so we can our main objective is to have a 3D segmentation, so we can contribute to an diagnostic by computer assisting by computers.
Do you think that the result will be not the same for the CT images?
We can have the same. I test this algorithm on the several medical images from different scanner, and we have the good results, but we can adapt this approach to the type of image.
Okay, thank you very much, Mr. Guskir. We continue with the paper ID 164, Mr. Stefano Rovetta.
Thank you. Good evening to everyone. I will share my screen now.
Okay.
And I think you shouldn't see anything by the moment.
Yes, not yet.
Do you see something?
Yes, it's okay.
Okay. So I am, as you...
Not yet.
No, it's okay.
It was okay. Okay.
I am Stefano Rovetta from the University of Genova, Italy. And in this talk, I will present joint work with Grażyna Szukaszka from the University of Opole in Poland, along with my colleagues Alberto Cabri and Francesco Masulli of the University of Genova. I will describe a project about feature selection for improving classification performance in a bot recognition task. In this work, feature selection is cast as a multi-objective optimization problem, and we solve it with a stochastic search meta-heuristic. Now, to the problem of bot recognition. We usually think of the internet as a means for people to communicate. Actually, a large fraction of the internet traffic, which is estimated around or even above 50%, more than half, is actually generated by bots. What are bots? Autonomous web agents, or web robots, or bots for short, are automated programs that usually perform boring tasks that humans don't want to do. For instance, gathering information for search engines or cleaning up the content of websites like Wikipedia. However, many web bots perform illegal or unfair actions like mass buying tickets for events or distorting advertising statistics with fake clicks. So here comes the bot recognition problem. Web servers receive requests from clients such as, for instance, your web browser via the HTTP protocol. Our goal is to recognize bots by looking at these requests after having grouped them into sessions And then after sessions have been identified, they will be recognized or labeled offline as being performed either by a human or by an automatic program. Requests are logged and stored in a text file in the server, complying with the predefined format, which is set up in the server configuration. And from the information, the pretty rich information that is contained in these log files, we can compute several kinds of features that describe sessions themselves. So the problem that we want to solve is, given the features describing one session, we want to label the session as performed by either a legitimate human user or a bot. And we want to find a set of features providing good classification performance while being as economical as possible, which means small. This is an instance of the classical feature subset selection problem. There are many types of feature selection problems that we can distinguish by, for instance, the desired result. We may wish to obtain ranking of the features from the best to the worst, from the most suitable to the less suitable, or simply taking a subset of the whole set of available features. We can also distinguish problems by the goal, the final goal, because in addition to improving classification performance, we may want, for instance, to reduce the size of the data for economy or for gaining insight into the problem at hand. In general, given a feature selection method, this will be defined by a quality criterion or metric, by a search strategy, and by an evaluation strategy to evaluate the quality criterion. Now, in our case, we are in the feature subset selection problem, and there are still restricting ourselves to this domain. We already have many choices. One of these is by search strategy. The search may proceed by forward selection, adding one feature at a time, or backward elimination, removing one feature at a time from the complete set, or forward and backward in the two directions. For evaluating the quality matrix, we can choose a filter approach. A filter approach optimizes some predefined quality index, which is computed beforehand, so without trying to classify using those features. Alternatively, we can use a wrapper approach, which optimizes classifier performance directly, using performance itself as a quality metric. This needs multiple retraining, so it's computationally expensive, the most computationally expensive strategy, but on the other hand, it is the most reliable of all, because the quality index that we are optimizing is the quality index in which we are interested. Then there are embedded methods, which can be used only if you have a classifier that already includes a feature selection part, feature selection subroutine. Now, for feature subset selection, we have to optimize for feature subset selection for classification. We have to optimize, of course, the size of the selected set of features. This is our first index of quality, but then there must be also indicators of performance. So we should add usually a pair of other indicators that allow us to measure performance on the positive class and on the negative class. And so we can try to find a good balance between false negatives and false positive. And this in this research, we have used precision and recall, which are very popular. In other words, feature subset selection in our problem statement will be multi-objective. There is another aspect of feature subset selection, which is the representation of the solutions. We will represent our features as a string of bits. Each bit will determine whether a given feature is present or not in the selected pool, as you can see in this animation. The size of the search space is therefore exponential in the number of possible features. So we need some smart strategy even to simply explore this space. So our proposal is to cast this problem. Okay, I'll come to it in a minute. What is multi-objective optimization? This specific type of optimization deals with problems that are defined by more than one objective function, as in our case. These objectives are usually conflicting. So if you optimize one of the available objectives, usually you decrease the other objectives. However, they must be optimized simultaneously. The output from a multi-objective optimization problem is a set, which we call pi, capital Pi, of Pareto optimal solutions. Pareto optimal solutions is a definition that allows to declare that a set of solutions are in some sense equivalent to each other. So equivalence is defined by this relationship. Solution X is Pareto optimal if, according to all objective functions, this solution is not worse than any other solution. This is the first inequality. And at the same time, according to at least one objective function, it is better than any other solution. And this is the meaning of the second inequality. Another name to declare that the solution is Pareto optimal is non-dominated solution. Now we have seen that we have a discrete search space which is made of bits. In this case, there is a classic. We have the availability of a classic meta-heuristic optimization method which is suitable for discrete optimization, and this is called simulated annealing. Simulated annealing comes from it is inspired by a metalworking technique which is called annealing simply, by which the temperature of a piece of metal is raised and then left to decrease slowly. In this way, the internal structure of the material will reach a low energy configuration, and we can apply a similar procedure to find configuration in the optimization space of an optimization problem where the objective function value is low. So this is a typical, probably the first meta-heuristic global optimization method. So the goal is to stochastically explore a discrete optimization space. What is the individual step of this iterative algorithm? We start from a solution. For instance, we are at a certain point in this search and we have a current solution X. Now we look for a candidate solution over line X, and we compute the probability of accepting this candidate solution as a function of the objective function in the present solution, current solution, and in the candidate solution. So this is the meaning of this computational P. So if P is larger than 1, it means that going from X to overline X, we have improved the objective function, and so we accepted the new solution, the proposed solution, with certainty. If the objective function has decreased, is worse in the proposed solution than in the present solution, then we may still accept the solution with a certain probability P computed as the minimum of these two terms. The exponential function assures us that if the worsening is very high, the probability to select this new X over line X is very low. However, if the quality of the new proposed solution is not so much worse than X, we have a high probability to accept it. We have a parameter T, which is a so-called computational temperature that is gradually decreased at each iteration. Now, there is another type of variant to the simulated annealing meta-heuristic, which is deterministic. it turns out that we can average the random choices that are being done in the traditional simulated annealing, and accept the current, we accept a new proposed solution over the current solution if the difference, the decrease in quality as measured by the objective function is less than a given threshold. So if it is negative, of course it will be accepted. But if it's positive, if we are increasing the objective function, we can still accept the new proposed solution, provided it is the worsening is less than a threshold tau. T. There is another kind of variant of simulated annealing, which is multi-objective simulated annealing. There are many ways to do so, and in this case we can see a couple of variants to the traditional stochastic acceptance procedure. Two examples of probability of acceptance with multiple objectives. The first one only accepts with certainty solutions that improve the current one. In the second case, we can also accept solutions that neither dominate nor are dominated by the current one. So if you cannot decide that the solution is not improving, this is called a situation of non-comparable solutions, you can still accept them. So these are two possible cases, and many other options are possible. Now, note that since objectives may not be comparable in range, we have to scale them by using these weights W that you see in the exponent. By combining these two ideas, we have created the multi-objective threshold accepting method. The method revolves around the concept of quasi-dominated configurations. We will say that solution X quasi-dominates solution Y if, according to all objective function, X is not worse than Y by more than a threshold tau. And this is the first inequality. And the second inequality says that there must be at least one objective function according to which X is better than Y. This definition is completed by inserting weights into the equations. So now to complete the algorithm, we have to add a rule to build the solution set. And this rule reads as follows. Every accepted solution, so every solution that obeys the previous inequalities that I have just explained, the weighted version, is added to the current Pareto set pi. By doing this, not all solutions are guaranteed to keep pi a real Pareto set. So after the end of the optimization, all non-Pareto optimal solutions in pi are removed afterward. Now we can move to the experiments that we have performed to test the effectiveness of the proposed method. First of all, the implementation. We used a wrapper strategy, which means that at every iteration we have to compute a classifier. The three objectives are, as I already noted, feature set size that must be minimized, and then precision and recall that must be maximized. This means that feature set size will have a positive weight and precision and recall will have a negative weight. The optimization space is composed of all bit strings of length 50, and the neighborhood in which to randomly choose a new candidate solution, we don't want to go too far from the current solution. So we decide that we restrict ourselves to a radius, to a Hamming radius of 3. So the neighborhood is defined by all the solutions that have Hamming distance at most 3 from the current solution, which means that we can find a new solution by changing the value of 1 or 2 or 3 random bits, randomly chosen bits in the current solution, current configuration. We have produced a parallel implementation using 20 processors. Actually, these are 20 cores in a server machine that we have for this purpose. The implementation uses the middleware MPI-CH. And the classifier that we used was the classical one nearest neighbor rule. This is not only because it's computationally inexpensive, but also because in a previous study, we have found that the nearest neighbor rule is a good classifier for this problem. So it's competitive with the more sophisticated methods. Now the results. This is a plot of the Pareto front. The Pareto front is supposed to be a line in the optimization space. Sorry. Actually, this is not a representation of the optimization space, but it is a projection in 2 dimensions of the space, which is 3-dimensional. To have a 2-dimensional plot, we have combined precision and recall into F1, the F1 score, which is their harmonic mean. So in this case, we don't have a perfect line in the plane. We have an approximate noisy line. We can observe that the highest values for F1 are reached for the smallest number of features. F1 is in the vertical axis and number of features in the horizontal axis. So if you go in the leftmost solutions, you see that F1 is highest. So this means that at least in this region of the search space, increasing the dimensionality of the feature set does not help. Or in other words, the objective functions were in synergy rather than in opposition. Let me remark that this is just this observation is valid just for this region of the optimization space. We cannot assume that it is like this behavior is found in all the space. We can zoom in on the leftmost solution in the graph, which is the one with the highest value of F1, and we can obtain the list of features that have been selected for that particular case. So you can see what is the output of this algorithm. The cardinality of the features is, okay, I can show it now. This is a table that tells us which are the specific objective values for this solution. Recall is 0.98, precision in 0.97, and the number of features is 20. So 20 is the size of the set of features that is deemed optimal according to this procedure. So for the conclusion, we have seen that the feature selector problem can be cast as a multi-objective optimization problem, and we have studied in particular the search component by proposing the multi-objective threshold accepting method, which was not present in the literature to the best of our knowledge. What remains to be done is to use this method to actually find important features, so to put it at good work, and to see whether the classification actually improves. And there are other aspects on the computational side, which are we wish to improve the performance on the algorithm that we have already implemented, so we wish to improve the parallel implementation. And we wish to speed up the computation of a more sophisticated objective function using a surrogate objective technique. And this is all. Thank you for the attention.
Okay, thank you, Mr. Stefano, for your presentation. Has someone any question for Herr Stefano?
I have one question.
Yes.
Thank you for clarification and your explanation and presentation. I have one question. Why you use the simulated annealing algorithm, knowing that it cannot be sure if it has found an optimal solution? So if you want to find an optimal solution, you must implement a branch and bound method. And why we can you don't test try to use NSGA 2 or 3 algorithm?
Yes, of course. Okay, as I said before, this algorithm needs further refinement because our goal was to find a procedure for the search of a suitable set of features, not so much to propose a new optimization algorithm, which was a good side effect. Regarding alternative algorithms, I needed the problem with local search algorithms like branch and bound is that they don't scale so well in very high dimensional spaces. And in addition, the feature selection problem, I don't know, but in previous experiences, we found it to be strongly non-convex. So there are many sets of solutions which are more or less equivalent in terms of the objective function. So given all these problems, we resorted to a stochastic search algorithm. And this is the reason why we worked on simulated annealing. Regarding the comparison, yes, we can try.
Okay, thank you.
Thank you for the question.
Okay, thank you, Herr Stefano. We continue with the paper ID 165, Nadia Raisi.
Hello.
Are you here?
I'm here.
Okay, you can begin, please.
Thank you, Professor Aitessin. I'm just trying to share my screen.
Please try to respect the time because we don't have enough time, okay?
Okay.
15 minutes, please.
Okay. Can you see my presentation?
Not yet, Nadia. Yes, okay.
Okay, so I'm not Nadia. My name is Soukaina Saber. I'm a PhD student in applied mathematics, and I'm working on the control theory applied to the dynamics of tumor cells and their therapies under the supervision exactly of Professor Nadia Raisi and co-supervision of Professor Mustafa Serhani. So my presentation is entitled Chemotherapy for Tumors. We choose a study of linear optimal control. So we will start with the motivation, then present the mathematical model on which we applied the control theory in order to characterize an optimal control, and finally illustrate the theoretical results using numerical simulations. So let's start by clearly defining what cancer is. Cancer is a term used to indicate a group of diseases that can affect any part of the body. This disease is characterized by a rapid growth of abnormal cells that grow beyond their boundaries and which can then invade a joint part of the body. And this process is referred to as metastasizing. So this phenomenon makes cancer a dangerous disease and the second deadly disease in the world. So finding a treatment of cancer is a cutting edge. That's why different disciplines contribute to fight cancer, including mathematics. For example, many researchers try to establish mathematical models that describe interaction between cells, especially tumor cells and effector cells. In this context, Kuznetsov and his team propose a nonlinear dynamics of immunogenic tumor to estimate parameters of the model and analyze the model. So our study is based on this model. So in general, the role of mathematicians is to better understand the interaction between cells, as I said, especially tumor cells and effector cells, to understand the development of this disease. And the other role, which is the role of our present work, is to propose treatments that are more effective and better adapted to the profile of each patient and his tumor, generating the least possible side effects. So to do this, we consider Kuznetsov's model that describes the growth dynamics and the interaction between two cell populations. We have tumor cells and effector cells. So tumor cells are noted by T and effector cells by E. So in this dynamic, the growth of effector cells is modeled by an affine function Fe, which is a constant flow of an effector cells, yes, and D, the mortality rate of the effector cells or immune cells. However, we consider a logistic function ft to describe the natural growth of tumor cells, where A is the maximum growth rate of the tumor cell population and the inverse of B, the maximum number of cells due to competitions for researchers. So these competition between cells are modeled by mice NTE and mice MTE, which mean that effector cell kill tumor cell by N rate and tumor cell can kill effector cell by M rate or deactivate effector cell by M rate. So the model takes also into consideration the stimulation of effector cells by the presence of tumor cells. This phenomenon is modeled by the function ft that depends on the state variables t and e to characterize the rate of accumulation of cytotoxic effector cells in the tumor cell localization region, where ρ is a maximum growth rate of the effector cells and G a half saturation constant. So the dynamic system of Kuznetsov is therefore given by the following model. And we can notice that in this model, we don't have treatment. So in order to support the partition in their choice of therapy doses, we add to this model chemotherapy treatments. So to do this, we insert a variable control that depends on time and in this model and obtain the following controller dynamic system. So the goal of chemotherapy treatment is to attack the growth factors of cancer cells and stop their proliferations. However, it also attacks healthy cells, including progenitor cells, which produce effector cells, so the immune system becomes, therefore, also affected. That's why the variable C that describes the concentration of chemotherapy eliminates tumor cells with mu rates and effector cells with H rates. And you admit that the concentration of chemotherapy should not exceed the maximum threshold and is limited as follows. So C should be in the set U of control. So this work consists in applying control theory on the controlled dynamic system. In general, the role of control theory is to analyze the property of the controlled dynamic system on which we can act on a control and also characterize an optimal control using Pontryagin's maximum principle, which provides first-order necessary conditions for a control to be optimal. So remember that the goal of this work is to find an optimal control C associated with the dynamic system that minimize an objective function G. So in our case, we define the objective function G that is linear in the control as flow, or by the following expression. So the problem is to minimize the objective function G, and minimizing the objective function G allows us to minimize the density of tumor cells and the total amount of chemotherapy drug given in the time interval 0 TF. So since the density of tumor cells and treatment doses do not have the same order of magnitude, we need to introduce epsilon, which is the scaling factor. And this allows us to display more clearly population dynamics with one objective function. So now, for the existence of optimal control, we should rewrite the controlled dynamic system using the following four, where X is a variable state and U a variable control, and the function F1 and F2 are the dynamics, respectively, of tumor cells and effector cells. So we establish the existence of an optimal control by using the following existence theory. So for each control, there exists a unique solution of the dynamic system studied. And there exists also an optimal control that minimizes the objective function G. So to prove this theorem, we need to prove many conditions. Firstly, the dynamic F should be continuous for all control and Lipschitzian with respect to the second variable, which is the control. And moreover, the set of control U should be closed and convex, and the dynamic F should be linear with respect to the control, and the integrand of G should be continuous, convex, and bounded. So now to apply Pontryagin's maximum principle, we need to define the Hamiltonian H associated with the dynamic system as follows, where lambda is an absolutely continuous application called a joint vector, and lambda 1 and lambda 2 defined by their derivatives, as you can see. So according to the Pontryagin maximum principle, the following equations are satisfied for almost T in 0 Tf. For example, from the second equation, we define the derivatives of lambda 1 and lambda 2. So in this case, the switching function is defined as the derivative of the Hamiltonian with respect to the control C, and the optimal control depends on the sign of the switching function phi. It's equal to 0 if phi is strictly positive, equal to 1 if the switching function is strictly negative, and there exists a singular optimal control if phi vanishes on an interval. So let's assume that C is singular on an interval T1, T2, which means that the switching function phi can vanish on the interval T1, T2. So from phi equal to 0 and its derivative equal to 0, we can write the adjoint variables lambda 1 and lambda 2 in terms of the state of the variable state T and E, and we get the following formula. So we can note that the expression of lambda 1 and lambda 2 depends only on variable states T and E and the parameters of the model. Then, after deriving a second time the switching function, we obtain an expression in terms of the states where the control C appears. So just to simplify the formula of the second derivative of the switching function, we define R1, R2, S1, S2, P1, P2, Q1, Q2 as follows. So now, before characterizing the optimal control, a necessary condition of Legendre-Clebsch should be satisfied, where 2 is the order of the singularity of the control C. After this, and under this condition, the second derivative of the switching function equal to 0 gives us a formula for the singular control in terms of the state variable T and E, and we get then a feedback control defined as follows. So after the characterization of the optimal control, we make at this stage numerical simulation to illustrate theoretical results. So to do this, we use a direct method of solving a minimization problem with equality constraints and inequality constraints. So equality constraints are the dynamics of variables T and E, and inequality constraints ensure that the control variables is bounded to be between 0 and 1. We use also the initial condition T0 is 0 and the values of epsilon equal to 10 power 6. So for the values of parameter, we use parameter values given in the following table with their units and the reference from which we take each value. We take the values of each parameters. So the following figure shows the optimal trajectories for tumor cells, effector cells, and chemotherapy treatment for 1 month. So we can notice that the optimal control in this run is bang-bang. And in this case, a maximum dose of chemotherapy is given at the beginning of treatment to reduce the density of tumor cells to a much lower but no zero level, which means that we do not eradicate the tumor cells at the end of treatment, but just we reduce their density. After almost 1 week or just 5 days, the medicine is shut off during the rest of treatment period, while the immune cell populations have a chance to recover and keep the tumor regrowth rate low. So as a conclusion of this work, we verified the existence of optimal solutions, and then we applied Pontryagin maximum principle to characterize an optimal control. And for parameter values we were able to find a therapeutic protocol that minimized the density of tumor cells at the end of treatment during 1 month. And finally, one perspective of this work is to consider the cost of treatment and patient comfort. So in next work, we approach this issue as part of a multi-objective problem. So thank you for your attention.
Okay, thank you very much, Ms. Sukaina, for your presentation. Has someone any question for Sukaina? If not, we continue with the paper ID 68, Mr. Rabbit. Are you here?
Yes, I am here.
Okay, you can begin, please. We don't have enough time. Only 15 minutes, please.
Thank you. Thank you. Good evening. Let me briefly introduce Israel, and I am delighted to be here today to talk to you about a numerical study of indoor air quality in ventilated room. My presentation is divided into 4 parts. First, I will talk about general of radon. Then I will present the physical and mathematical model. Next, numerical method. Then we present the result and discussion. And finally, the conclusion. Let me start with some general information on radon. Radon is invisible, outerless, titleless radioactive gas. It is formed by the disintegration of radium, which is a decay product of uranium. Radon emits alpha particle and produces several small radioactive products called radon daughters. Some amount of radon gas and radon daughters are present everywhere in the soil, water, and air. Particularly high radon level occur in the region where the soil or rock is rich in uranium. Radon is emitted by radium in the groundwater, and building material. It can enter to indoor air, where its decay products accumulate in poorly ventilated areas. Harmful level of radon and radon daughters can accumulate in confined airspace, such as basement and crowd space. Radon daughters are inhaled with air and deposited in the lung. The lung absorbs alpha particles emitted by the radon daughters. The resultant radiation dose increases the risk of lung cancer. The radon concentration level are seen to vary significantly from house to house and as way to time and season. This type of variation are also seen in the underground construction. It is found that the radon concentration level are high in underground construction, where water is present due to the ability of water to transport radon. The study focused on investigating numerically to influence of environmental condition on indoor radon concentration and spatial distribution. The studied model physics is illustrated in figure 4. The classical mass moment energy and radon concentration equation can be represented for a steady-state three-dimensional flow with the fluid equation. Table 1 shows the boundary condition for the physical model. The inner light and outer light of the room were set for constant velocity and pressure condition, respectively. The indoor wall were set for non-slip condition. The system of equation weight with this variable is numerically solved with finite volume method. The result will be exposed in three axes. The effect of ventilation on indoor radon concentration. After we present the effect of halt flux on indoor radon concentration. Then we present the effect of position of outlet on indoor radon concentration. Figure 5 illustrates the effect of ventilation on indoor radon concentration for different value of Reynolds number. We observe that the radon concentration is rapidly decreased in vicinity of the low and life wells. This decrease is caused by the introduction of fresh air. The simulation results are summarized in table 2. In this table, we can observe that the ventilation decreases radon level in the room. Figure 6 illustrates the influence of height flux on indoor radon concentration. We note that the more of Rayleigh number increase, the more of diffusion of radon concentration is important. Table 3 gathers the average value of radon concentration inside the room, studied according to the Rayleigh number. We observe that the temperatures as well as average concentration increase progressively with Rayleigh number for the 4 configuration. In this figure, we can show that the configuration 4 gives a better quality of air. This indicates that it evacuates to radon significantly. This shows that the configuration 4 ensures good air quality. Finally, using this model computational fluid dynamic, it's possible to determine the indoor distribution of radon and its doses. Therefore, it is good tool for assisting radiation dose to enable the individual from the index of radon data indoor. And thanks for your attention.
Thank you very much, Mr. Rabbit. Has someone any question for Mr. Rabbit? No questions? Okay. I want to thank you all. We will end this session.
Thank you very much.
You are welcome to closing ceremony about 16:45.
Sorry.
Thank you very much. Thank you for.
Hello, Chair. Hello, Chair.
Yes.
My name is Mukhtar. I missed my presentation in the morning, and I was asked to join this session. So yeah, paper 55.
Paper 55.
Paper ID 55.
Which ID, please?
ID 55. 55.
55. One moment, please.
Yes.
Mr. Mukhtar?
Yes, Chair.
Do you hear me? Yes, we can. You can present now. Okay.
Okay. Okay. Thank you.
Okay. You can begin, please. You have
Can
only
you
12
see
minutes,
my-
please.
Okay. Can you see my presentation?
Yes, the full screen, please.
Okay. Yeah, my name is Mukhtar Alaimi. The title of my presentation is Comparing the Legenda Wavelet Filter and Gabo Wavelet Filter for Future Extraction based on iris recognition. This is the content we're going to go through. Introduction, literature to conclusion. Now, iris recognition falls under biometric technology. Biometric technology is measuring and analyzing biological data, mathematical method of recognizing an individual. Now, this iris falls, there are two characteristics of biometric. There's physiological and there's behavioral. Now, iris recognition falls under physiological characteristics. Now, what is an iris? Iris is the region that is in between the sclera and the pupil of every individual. Now, the iris recognition pattern recognition technique based on high resolution of images or of an iris images. Today, iris recognition is considered as one of the most secured and the most accurate form of biometric technology. Now, there are two types of this recognition. There's active and there's passive. Now, the passive is when the individual is a little bit closer to the camera, while the active is when you're a little bit away from the camera. Now, this whole idea about iris started in the year 1936. But the first system was developed by John Dogman in the year 1987. Now, what is the problem? Presently, they are one of the most used form of biometric technology is fingerprint and facial recognition, and presently facial recognition have some setbacks because with time people facial characters change, and it's become difficult for an old registered or the biometric sometimes get there and with one device that other people touches. Now, the main problem with the iris now is recognizing the individual with either an image that is not well captured or it's from a distance. Now, the iris recognition process is based on the first thing in iris recognition is to capture the eye image, because there's a very small eye region in the eye. It's difficult to get a camera that can extract only the iris out. So the best the camera can do is to get the entire eye image. Now, the next thing to do is to segment the iris from the entire eye, and there are a lot of methods you can use to do that. There is an integral differential operator, phase transformation, and many more. Next is the normalization of the iris. Here, the spherical iris is converted into rectangular form. Now, there are also rubber sheet method and other methods used for it. The next thing is to extract the features, this unique feature of the iris from the iris template. Now, there are a lot of algorithms that are used for this. One of them is the 2D Gabo wavelet filter. Wavelet filter itself is used, and this is where our research is going to lay emphasis on. Now, after the segmentation and normalization, the iris code is computed based on the information received from the wavelet. Now, a wavelet is a mathematical function useful in digital signal processing and image compression. The use of the wavelet for this purpose is a recent development, although the theory is not new, and the principles are similar to those of the Fourier transformation, which were first developed in the early 19th century. Now, after that, we look at other wavelets, since the Gabo wavelet filter is the most used, and we found out that the Legenda wavelet filter has more similarity compared to other wavelet filter. Now, the whole objective was to design the iris framework based on the two Legenda wavelet filter, then to develop and then later evaluate the accuracy of the system. And this is the flow of our research process. So the first thing was we took the Legenda wavelet filter, and we took the Legenda wavelet, we converted it into a filter, and this work is published already. And so we also plotted the Legenda wavelet filter in three different degrees. We plotted in the first degree, third degree, and the fifth degree. However, we only used the first degree of the Legenda filter. Now, these are the filter we designed for the wavelet filter, Legenda wavelet filter, and this for the dimension of the future vector to be used. And first thing we did was look at the database that are used for the evaluation of the iris or iris recognition, and we found out that the CASIA, almost 90% of the research reported on iris recognition using a database, and that's why we said so the UBA database is one of the a database with more complicated iris images that are not well captured. We also use it, and we also use the database from the Multimedia University in Malaysia. So after all these things, after we develop the system and we select the database, we look at what are the things we going to evaluate our system with. Now, the first thing is to check the force acceptance rate. This occurs when an unauthorized identity is being granted access by the system. That is to say, if someone came with a false identity, that's this, and he came to be the right person, the system allowed him. Now, the next thing is the false rejection rate, when an authorized identity is rejected by the system. Now, lastly is when a genuine identity is granted access to the system. So the first thing we did was we plotted the Legenda wavelet filter with the dimension of n equals to 1. We look at the result. We did the same thing for the Gabo filter. We also plot the dimension of the Legenda wavelet filter to be 10. We did the same thing with Gabo filter. From here, you could see the result for the Gabo filter was already not very good as we expect, and we did it when the both dimensions are equals to 20, and there's not even any physical result from the Gabo filter. We did it until the dimensions are equals to 40. Now, because we took the CASIA are they have different subsections, so we took only two sections, the interval and the distance, and we plotted. We tried to run the Gabo wavelet filter, and the the accuracy of the system was around 7.6. Then we used the Legenda wavelength filter we developed, and the accuracy was around 8.20. Now here there is no much significant difference between the Gabo filter and the Legenda filter. We did the same thing with the distance. However, when we use the UV iris data set, for the Gabo wavelet filter, we're able to achieve an accuracy of around 80.020%. For the wavelets, for the Legenda wavelet filter, the accuracy was up to 85.60. Now here there's a significant difference between the Legenda wavelet filter and the Gabo of almost 5.40, and we did the same thing with the MMU database. So the Legenda wavelet filter was compared with the Gabo wavelet filter based on its efficiency and accuracy of their operation, and a significant increase was achieved. The feature of the research is to compare the Legenda wavelet filter with other feature extraction technique. Thank you very much. I will take questions and answer now. Hello?
Hello, Herr Mukhtar?
Hello.
Yes. Okay. Thank you very much, Herr Mukhtar, for your presentation. Herr Mukhtar?
Yes, I'm here, Chair.
Hello?
Hello, can you hear me? My network is it's not very good.
Okay. You give your conclusion and we. Okay. Thank you, Herr Mukhtar, for your presentation. If someone has question for Herr Mukhtar. Okay, thank you very much. We will end this session. You are welcome to closing ceremony now. Thank you very much. Join the session for the ceremony, please.